Chapter 8, Introduction to Hypothesis Testing, Part 7. In a previous video, we discussed some of the limitations of conducting a hypothesis test, specifically the Z statistic that we calculate. And we talked about the influence of sample size on that Z statistic. And we discussed how changing the size of the sample will influence the ability to reject the null hypothesis. So for example, we discussed that as n increased, the standard error of the mean decreased, and our Z statistic increased. And when we have a larger Z value, again, thinking back to our normal distribution, the value of that Z-score, the larger it is, the more likely it is out in the tails of the distribution, which then results in a higher probability of rejecting the null. So as a solution to that flaw, we learned about calculating Cohen's d. So Cohen's d, instead of expressing the location of that Z statistic in standard error units, we use Cohen's d to express the difference between the sample mean statistic and the population mean in standard deviation units. So our d statistic is equal to our sample mean minus our population mean divided by our standard deviation. So opposed to what we saw in our Z equation, our Z was equal to m minus mu divided by the standard error. And we know that standard error is a function of our sample size, which again lends itself to a bit of a limitation or a flaw because we recognize larger sample sizes are going to increase our Z value and again increase the likelihood of rejecting the null. So Cohen's d helps us express the difference between the treated group and the untreated group. So it takes out the influences of sample size, and we refer to Cohen's d as a measure of effect. And again, it helps us illuminate if we've made any errors, whether we've engaged in a type 1 or type 2 error. In other words, if we have a very small d, but we rejected the null, then that should give us pause and make us question the conclusions that we've drawn based on our Z statistic. So again, I just wanted to review that briefly, that again, there are limitations of the hypothesis test, mainly the influence of sample size will increase. As n increases, the likelihood of rejecting the null increases. And so a way of doing away with that flaw, or addressing that flaw is a better way to say it, we calculate Cohen's d. And again, Cohen's d is going to express the mean difference or effect size in standard deviation units. Now, instead of measuring effect size directly, an alternative approach to determining the size or the strength of a treatment effect is to measure the power of the statistical test. The power of a test is defined as the probability that the test will reject the null hypothesis if the treatment really has an effect. So again, I'll restate that the power of a test is the probability that the test will correctly reject a false null hypothesis. Now, normally, calculating the power is done prior to collecting data or prior to involving yourself in stating the hypothesis, collecting data, calculating your test statistic, and drawing conclusions. It saves the researcher time because it gives you a preview as to what may potentially happen. And the larger the power, the more likely it is that you will have a successful research scenario. So again, power is usually estimated before starting a study and serves as a mean of determining whether a research study is likely to be successful. So before we go on, we should review the concepts of type 1 and type 2 error. So our type 1 error is defined as when a researcher rejects the null hypothesis that is actually true. So the researcher is saying that there is an effect when there really is not. And a type 2 error is defined as the researcher failing to reject the null when the null is false. And we can interpret that as the researcher is indicating that there was no treatment effect when there really was a treatment effect. We also learned that type 1 can also be determined by our alpha level, or in other words, our alpha level sets the probability of engaging in type 1 error. So whatever alpha is, let's say we determine we're going to test our hypothesis using alpha at 0.05, we then would conclude that there's a 5% chance that we're going to commit a type 1 error. And that is simply saying that when we look at our normal distribution and our critical region is set, and again, if it's total equal to 5%, again, we recognize that in that normal distribution, those sample means do exist. They exist in very small numbers, meaning their probabilities are very small. So if our untreated population mu is here and we obtain a test statistic out here in the tail, again, it may be that by chance we selected a sample mean that already existed in the tails. It was one of the extremes of that distribution. But because it's so different, right, these values are so different, and because that sample mean is in the tail, we rightfully conclude that we get to reject the null hypothesis. But again, recognizing that that value may have just occurred by chance and we've committed a type 1 error. Again, that error could be illuminated by computing our Cohen's d. If we have a very low Cohen's d and we reject the null, then that gives us reason to go back and look at our research and assess whether or not there truly is a treatment effect or not. So again, we learned that alpha is the same as, or our alpha level is the same as our type 1 error. Unlike type 1 error, it is impossible to determine a single exact probability for type 2 error. Instead, the probability of type 2 error depends on a variety of factors and therefore is referred to as a function rather than a specific number. Nonetheless, the probability of a type 2 error is represented by the symbol that we see here, and that's referred to as Greek letter beta. So in this point here, we're saying that our power, which we're going to learn how to calculate in this video, power is equal to 1 minus beta. And you may be wondering, what does the 1 represent? The 1 is the 100% under the normal curve. Again, if we turn that into a proportion, right, 100% is equal to a proportion of 1.00. So power is equal to 1 minus what our type 2 error is equal to, and also referred to as beta. Now again, as I just indicated, there's not a specific equation that determines type 2, or in other words, as we saw with type 1, we know that our alpha level is equal to the probability of committing a type 1. Instead, we can use power and take 1 minus the beta, or have our power value and subtract it from 1 to deduce what the type 2 value is equal to. For example, let's say that as we go through the example of computing power, let's just say that we concluded that power was equal to 0.70 or 70%. If that's the case, then let's figure out what beta is equal to. So again, our equation says power is equal to 1 minus beta. So if we replace variables, we would say that power is equal to 0.70, and that's equal to 1 minus our beta. So now we've just replaced our variables, and given this and our basic algebra skills, we can move things around so that we can solve for beta. And I'll give you a moment to try that on your own before I provide you the solution. Okay, so as you know, we would want to isolate beta, so we would add it on this side as well as on this side. And I apologize that this is a bit messy. And then we want to get rid of the 0.7 on this side, so we'd subtract it from that side and from this side. And then what we would end up with, so therefore we would say that beta is equal to 1 minus 0.70. So our beta would be equal to 0.3, or we would say that there's a 30% chance of engaging in a type 2 error. So again, unlike alpha that determines the probability of engaging in type 1 error, we don't have a specific value of what beta is equal to, but we can use these other variables. We can calculate power, and then we recognize that what we're talking about is the whole entire distribution, 100% or proportion of 1, and then use the variables we have to figure out what the probability of engaging in a type 2 error. Now, there isn't a lot of application or reason to do this, but you may have some mathematical problems in your homework that ask you to solve for beta given the relationship between these variables. But what I want to focus on now is actually how do we calculate power. Again, power represents the probability that test will correctly reject a false null hypothesis. And when we do calculate power, again, remembering that it's done prior to engaging in the test, prior to collecting data, because it's going to help determine how successful the research will be. And the power usually estimated before starting a study requires several assumptions about factors that influence power, such as sample size and the alpha level, which I'll discuss after I walk you through one example of how to calculate power. So figure 8.9 illustrates what we are trying to do when we're calculating power. So here in the center we have the original population with that has this is a mistake I just noticed. This is an error in the slide. So this should say the mu is equal to 80 and the standard deviation is equal to 10. So they just reverse those two. So we have an original population that has an average mean score of 80 and a standard deviation equal to 10. Now on the left, this represents if the null were true. Again, the null says no effect, nothing happened, the treatment was did not illustrate any change. And so if the null is true, again, we would anticipate the mu of that population to equal 80 and the standard deviation equal to 10. Nothing would change. And even if we used a sample, again, they're identifying that we're using a sample of 25 individuals that have been exposed to some treatment. But again, if the null is true, then the mu would remain the same, the standard deviation would remain the same, and we would note that there would be no difference. Now on the right side, we anticipate, let's say we're anticipating an 8-point treatment effect. And when you see this expressed that way, treatment effect, that's the same as saying m minus mu. So if that's the case, what would we anticipate our sample mean to equal? The sample mean meaning those who have received the treatment. So if we know that mu is equal, so if we have treatment effect, is equal to 8 points. So we're saying the difference between the two is equal to 8. So if m minus 80 is equal to 8, then our sample mean must equal 88. And that's where this value is coming from. Again, I am illustrating m as the sample, but recognize that that sample is always representative of a population, which is why we see mu here is equal to 88. So don't get confused or lose sight of the fact that we're always using samples to infer about a population. So technically speaking, we would express it as mu is equal to 88 because we anticipate whatever happens to the sample we would also see reflected in the population. So again, just to point out, whenever you see treatment effect, that's the difference between the sample mean and the population mean, or the treated sample and the untreated population. And so now, given this effect, notice the difference. So we moved from 80 to 88, right? And the standard error was calculated by using our equation of standard deviation over the square root of n. Standard error is equal to 10 divided by 25, because they told us we're using a sample of 25 individuals. So that's 10 over 5, and our standard error of the mean is equal to 2. So that's where the standard error of 2 is equal to. And what we've learned is that one of the assumptions is that the variability before and after treatment is equal, because the treatment effect is simply adding the same amount of points to each individual. And when we add and subtract a constant from our x values, the mean changes, but the variability does not. So again, that's one of the assumptions that we make when we're engaging in the hypothesis test, that the variability is consistent from the before and the after treatment. All right, and so what we have in this original distribution on the left is the untreated population mean, or if the null is true, no effect. And we are engaging in a hypothesis test where alpha is equal to 0.5, which is where the negative 1.96 and positive 1.96 z-scores are coming from. That is setting the critical region. Again, that alpha level is the same as saying the probability of engaging in type 1 error. So there's a 5% chance that if we get a value in the critical region, we are committing a type 1 error. We are falsely rejecting the null, or we're rejecting the null in error. All right, I'm going to rewrite all of this so that we can go step by step, but I just wanted to kind of identify what we're looking at, what it means to calculate power. And before I go on to another sheet, this blue area is representative, this area here, of the power, the probability of accurately rejecting the null. So if we see again, the left side indicates that the treated group would show no effect, and the untreated population mean would equal 80, and therefore we would require a z-score greater than 1.96 so that it falls into the critical region. And then if the treatment is effective and we have a population average of 88, now notice all the values that would be greater than 1.96 when we're talking about this second distribution. Now I know that it's a little confusing, but hopefully when I walk through the step-by-step process, in this case the power would be equivalent to the body once we calculate what that sample mean is equal to here, given the z-score. What is the sample mean equal to when we're talking about the treated population? And again, we know what the body looks like. It's the larger proportion. So at this point, we could conclude that the probability of accurately rejecting the null is pretty high just by visually assessing the value, or the probability or proportion of scores, I should say sample means, in that treated group that's illustrated in that blue area. Okay, so just to review, we're working with the original population with an average of 80, standard deviation equal to 10. We're going to select 25 individuals randomly and administer treatment. And we're projecting that that treatment is going to have an 8-point treatment effect. And the reason why it's 88 versus 72 is because in the text it says that we're adding 8 points to each individual score. In other words, we anticipate that this treatment increases individual scores, and that's very important. You need to pay attention to the research scenario. The treatment may be an antidepressant drug, and in that case the anticipation would be that we expect depression levels to decrease, so the effect would would result in a decrease. So pay attention to those types of words. Is it increasing or decreasing? How is it reflected in the treatment effect that's a given? In this case, it said 8-point treatment effect, but we had to go back and see exactly what that effect looked like. In this case, it was an increase. All right, so again, we have our normal distribution, our untreated population, and the average is equal to 80. And we did calculate our standard error before, but let's do that again. Standard deviation over square root of n, 10 over square root of 25, 10 over 5 gave us 2, right? So our standard error is equal to 2. And we identified that we're implementing alpha equal to 0.05. And we've learned that we don't even need to look that up anymore. We should know that that is the same as saying a critical region set at negative 1.96 and positive 1.96. And I'm actually going to rewrite that a little bit lower, because what I'm going to have to do is calculate what the sample mean is equal to at that critical region. So I'm going to have my z value down here of positive 1.96, negative 1.96. We don't really need to pay attention to the negative because we know it's an increase. The treatment effect increased scores. And what we need to do now is identify what's the equivalent sample mean value that's equal to 1.96 z-score. Because we know when we're calculating our z-statistic, we know that it has to be greater than 1.96 to reject the null. But looking at it from a different perspective, instead of saying what z-score do I need, I want to know what exactly the sample mean must equal so that I can reject the null. So we're going to transform that z-score of 1.96 into a sample mean. So the mean is equal to the mu plus or minus our standard error multiplied by our z-score. So let's replace variables. This is 80 plus or minus the standard error equal to 2 multiplied by positive 1.96. And what I'm solving for is this: what is m equal to? What is the minimum sample mean value I need so that I can reject the null? I should restate that. What value does it need to be greater than? So I'm going to calculate the cutoff point for the sample mean and recognize that anything greater than sample mean will place me in the critical region and enable me to reject the null hypothesis. So let's get our calculators out and calculate again 2 times 1.96 and add it to 80, and you should get 83.92. And so what we've just calculated is we converted that critical region z value into an actual sample mean value. So it's 83.92. And what we're saying is that if we administer treatment and our sample mean is greater than 83.92, we get to reject the null. Now, what did we anticipate the sample mean, the treated sample mean, to equal? We anticipate it to equal 88. So we know that we're going to definitely reject the null hypothesis if an 8-point treatment effect is viable. If that's really going to happen, then that puts us way out into the tail. Now, so this is the first step. The next step is in calculating power is to identify where that value of 83.92 resides in the distribution of the treated group. So let's consider again our treated population. And it's hard to draw this perfectly. Let me try that one more time. Move over just slightly. Now we anticipate the treated population to equal 80. And again, this was the critical region, our blue area. in the original population. And now we want to know, essentially, to calculate power, if this anticipated treatment effect of 8 points is true, now we can set up a probability statement that says the following. What is the probability of obtaining a sample mean greater than 83.92, right, if there is a treatment effect? So now we're focusing on this second distribution. So in order to do that, we're going to shade how this probability statement reads, and if this is the value of interest here, and it says greater than that value, now we're going to shade all to the right. So again, based on that other visual from the text, I said this is the body of that distribution, the treated population. So now our job is to find out what that proportion is equal to. The probability of obtaining a sample mean greater than 83.92 from the treated population that has an average of 88. So now what we need to do is convert that sample mean of 83.92 into a z-score. Z is equal to 80, our equation first, z is equal to m minus mu divided by standard error. And again, I'm writing in red because we're focusing on this treated population, so we must use the values that relate to that distribution. So z is equal to 83.92 minus 88. Now don't make the mistake of writing 80, because if you do, you'll end up with the original critical region z-score. You're just working backwards. So we need to recognize now we're talking about the treated population. So divide by our standard error. Again, the standard error is equal on both sides. So that's equal to 2. Again, the variability does not change. It's the same before treatment, after treatment, with treatment effect or without treatment effect. And so now in your calculator, take 83.92 minus 88, divide by 2, and we should get a negative value, negative 2.04. And what have we just done? What we've done is created this, we've converted this value into a z value as it relates to the new distribution. So I'm going to, just to make things a little easier to remember, put that in red. So again, when we calculated 83.92 originally, it was based on our alpha of 5%, which meant our critical region was set at positive 1.96. Then we calculated what the sample mean would be equivalent to a z-score of 1.96. That was this process here. And then we took that same sample mean and placed it in the distribution that illustrates a treated population. And now we want to see what is the probability of obtaining that sample mean from the treated population mean. And now we had to convert that sample mean into a z-score given the new parameters for the treated population. And so now our job is simply to answer this particular question. We simply need to utilize our unit normal table and report the body. And I know it's the body because of the shading. It won't always be the body. It may be the tail. It all depends on where these values are located in relation to the untreated population, the alpha level. All of these things are factors that play a part in determining the power of the test. So at this point, we're going to use that z-score and report the body, and then we'll have our answer for what the power is for this particular test. So here's our unit normal table, and our z-score of 2.04 is here, and the body is this area here, so 0.9793 is the proportion in the body. And what that means is that we've determined the power of this particular test. So I'm going to go back to the previous slide to put this all together. So restating that original probability statement using a z-value would mean that we have now determined the probability of obtaining the z-score that's greater than negative 2.04 is equal to 0.9793. And therefore, what we're saying is that if the treatment has an 8-point effect, which we anticipated, 97.93% of all the possible sample means will be in the critical region, and we will reject the null hypothesis accurately. So again, we're indicating that the body is representative of the power in this particular example, and there's a 97.93% chance that we will accurately reject the null hypothesis. Again, by definition, that's the power of the test, accurately rejecting the null hypothesis. So we now know what the power is equal to. We know the proportion of the entire distribution. So let's figure out what beta is equal to. So we know that power is equal to 1 minus beta. Again, beta is the probability of engaging in type 2 error. 1 is representative of the entire distribution, 100% or proportion of 1. This is 100%, which is the same as saying a proportion of 1.00. So if now we've determined the power is equal to 0.9793, and 1 remains the same, minus beta. We can figure out what beta is equal to. So beta would equal 1 minus 1.00, just to make it a little cleaner, minus 0.9793. So beta, the probability of engaging in type 2 error, is equal to, and our calculator is 1 minus 0.9793, gives us 0.0207. And so we've calculated this. Again, there's not a great application of this, but you may have some mathematical problems where you're asked to deduce what beta is equal to given what you've calculated for power and your understanding of the entire distribution. 100% is equivalent to a proportion of 1.00. Now if we go back to the original figure, which is a little cleaner and easier to read, I want to point out again that we've just done the exact same thing that you see here, and this obviously gives a little more detail. Notice the standard error is 2 points, and so they're counting by 2 here down on the abscissa, so by 2s. That's where these values are coming from. And we did calculate the sample mean in the original distribution. The sample mean that's equivalent to a z-score of 1.96 was 83.92. So notice its relation to that value of 84. It's slightly to the left, which would make sense. And then again, this was the body, this whole blue area was equal to 0.9793 or 97.93%. Was representing the power that there's a 97.93% chance that we will accurately reject the null, or another way of thinking about it is approximately 97.93% of all treated sample means would be greater than 83.92 if taken from the treated population. Now another thing I want to point out is what we started discussing at the beginning of this lecture was Cohen's d. So Cohen's d is m minus mu divided by standard deviation. So instead of standard error, we express it in standard deviation. And so this would equal 88 minus 80 divided by 10. So our Cohen's d would equal 8 divided by 10. Cohen's d would equal 0.8. And so now, instead of expressing the difference between the treated and untreated population means in standard error units, we're expressing standard deviation units. So let's think about this for a second. So again, we're talking about and focusing on the movement, right? The change from the untreated to the treated. How far is this distribution going to shift if they receive treatment? And now we've expressed that difference to equal 0.8, 0.8 of a standard deviation unit. And that should make sense given that the point difference, right, is 8 points, and the standard deviation is equal to 10, right? So we're saying, so 10 points is representative of one standard deviation unit. The shift was equal to 8 points, which is the equivalent of 0.8. So we know that given the table in the text that shifting over 0.8 standard deviation units from the original value is significant. It's considered a large effect size. So I just wanted to show you that again because we can express this effect size in different ways or think about it in terms of statistical power, effect size, but it's all relating to, do we see a huge shift and is it significant? Did the whole group move one way together, by increasing their values or decreasing the values, and is it far enough from what the original value was for us to feel as though yes, the treatment was effective? And now statistically speaking, we see that it is unlikely that this shift was due solely to chance. So here we're seeing a shift of 0.8 standard deviation units from the untreated to the treated. So that concludes this video. In the next video, we'll be talking about the influence on power, and I'll actually walk you through a demonstration of how sample size affects the power of a hypothesis test.